Alright, so in this video, we'll be looking at how to calculate the energy of a photon using the frequency. And so this is something that comes up quite a bit in general chemistry, physics, and AP chemistry. And so the math is very simple. We just need to look at the formula. So let's just break it down. So the main formula, or the core formula that you need here for photon energy is going to be E equals H times nu. And so here, our E is simply the energy of the photon. Energy of the photon. And this is going to be in units of joules. So this is going to be in units of joules. H, that is our, what's called Planck's constant. Planck's constant. And Planck's constant is equal to 6.626 times 10 to the negative 34. 10 to the negative 34 joules times seconds. Joules times seconds. So this is Planck's constant. And nu, the Greek letter nu, is going to be our frequency. Frequency. And it's important that we see that this frequency is also, we use the Greek letter nu, but it can also be denoted with the letter F. So both of these, can be used to show frequency. So this can be written as either E equals H nu or E equals H F. Both of these are the same. And so this is going to be our frequency, right? Is going to be in units of hertz. Hertz. And while we're on the subject, you can see that hertz, our unit of frequency, is equivalent to seconds to the negative 1. So, or 1 over seconds. And so any of these, if you see any of these, you should know they're all, equivalent. So there isn't really much conversion that needs to be done. You just need to change the unit. These are all, the same. So this is going to be hertz or seconds to the negative 1. And this formula basically is showing us that energy is directly proportional to frequency. Or in other words, the higher the frequency, right, the more energy. Oops. You can write it like this, right? The higher our frequency, or, frequency, whatever we want to use, the greater our energy is going to be. And this is pretty clearly delineated or, shown with this formula. So now let's just look at a couple quick examples of, finding the energy given our frequency. So what is the energy of a photon with frequency 5 times 10 to the 14? Sorry. This looks a bit unclear when I typed it out, but let's see. All right, so what is the energy of a photon with frequency of 5 times 10 to the 14 hertz? Well, this is, again, straightforward enough. We just need to start off with our formula, E equals H nu. We're trying to find our energy, and Planck's constant is a constant, so it's always going to be the same. That's going to be 6.626 times 10 to the negative 34 joules times seconds. And well, here our frequency is given as 5 times 10 to the 14. So that's 5 times 10 to the 14 hertz. And just for, the sake of demonstrating units, we can see that this is, if we wrote it in units of seconds to the negative 1, which again we know is the same as hertz, we'll see that, well, seconds to the negative 1 can be written as 1 over seconds. And then our units of seconds and seconds can cancel out. And that's why we get our answer in units of joules. And so multiplying these out gives us an answer of 3.313 times 10 to the negative 19 joules. And so this is going to be our energy of our photon. All right, looking at this next one, we're told that a photon has a frequency of 850 megahertz. What is its energy in joules? And so this is effectively the same as what we've seen previously. Energy is h times nu. The only difference here is that we're told our frequency, or we're given our frequency in units of megahertz as opposed to hertz. This is the same thing as if we had kilograms and we had to go to grams, right? So we just have a larger number of grams, and so we use the unit kilograms. Similarly, when you have a much larger number of hertz, we can use megahertz, terahertz, gigahertz, and so on. And so it's just important that you know your prefixes here. And so in this case, 850 megahertz, well, that's the same thing as 850 times 10 to the 6th. So that's what this unit of megahertz, the prefix here, it tells us. And we can write this in scientific notation by just saying 8.50, right? 8.50 times 10 to the 8th hertz. So this is the number of hertz that we're dealing with. Now we have our frequency. Again, remember Planck's constant is going to be staying the same anyway, so that's just going to be 6.626 times 10 to the negative 34 joules times seconds, times, now we just have our frequency, right? We calculated that, or we converted that from megahertz to hertz, and found that to be 8.5 times 10 to the 8th hertz. And then multiplying these out gives us our answer to be 5.6321 times 10 to the negative 25 joules. So this is going to be the energy in joules of our photon. All right, let's look at one last quick example. So now we're told that if one photon has a frequency of 6 times 10 to the 14 hertz, we have to find out how many of these photons would add up to 1 joule of energy. So first, we can start off, as we would with any other problem, by finding out first the energy per photon. So our energy per photon, again, can be found using the formula that we become accustomed to in this video, which is energy equals h times nu. Here, again, Planck's constant stays the same. 6.626 times 10 to the negative 34 joules per second, times our frequency, which is 6 times 10 to the negative, 6 times 10 to the 14 hertz. This gives us our answer, or not our answer, but this tells us that each photon here then will have an energy of 3.976 times 10 to the 19 joules. And well, if we're trying to find the number of these photons that would add up to 1 joule of energy, well then this number of photons, we're simply going to have to divide 1 joule by the energy that each photon has. So divided by 3.976 times 10 to the negative 19 joules. And this is going to give us an answer of 2.514 times 10 to the 18 photons. So about 2.51 times 10 to the 18 photons of this that have this frequency are going to be needed to make 1 joule of energy. So that brings us to the end of this video. I hope you found it useful. Keep an eye out for our next video. We'll be talking about calculating energy given our wavelength. And in the meantime, again, if you found this helpful, please show your support by liking and subscribing, and I'll see you guys in the next one.